Alright, so I'm going to start our next video here on the systems of differential equations. And so by system, I'm going to talk about autonomous systems because, as it turns out, you can write any differential equation as a system of autonomous differential equations. So how would you do that? If I had something like x prime equals x plus t and y prime, equals y plus t squared, just for an example, then it's kind of, you might think it's cheating, but you can just write t as a new variable. Just let z be equal to t, so that z prime is just equal to 1. And so then you would have x prime equals x plus z, y prime equals y plus z squared, and z prime equals 1. Okay, and so it is possible then to write our system just as a autonomous system. Okay, now how do we solve an autonomous system of differential equations? There are several methods to do this, some of which we already know. One, we might be able to solve by forming dy over dx instead of dy over dt and dx over dt. That is, dy over dx would be dy over dt divided by dx over dt. And so in this case, that would be g of xy divided by f of xy. Now we're not guaranteed that we'll be able to solve this from chapter 2, but we would hope that we would. Right, that's just the goal. We might be able to. Secondly, if it's linear, then it's possible to rewrite this to a second order differential equation, and we could solve it using chapter 3. Right? By that I mean it's y double prime, or ay double prime plus by prime plus cy equals 0. Good. So those are a couple ways we could solve a system of differential equations right off the bat. Sometimes we just get lucky. If it's... let me pause for a second. So what I mean by that is if x prime only depends on x, and y prime only depends on y, this would be said to be uncoupled. And so you could just go through and solve each of those separately, right? And then just put them together as a system. So just for a quick example, x prime equals x, y prime equals y. Yeah, these are two separable differential equations now that we could solve. Okay, anyway, so uncoupled differential equations we can solve pretty much right off the bat. Okay, and then the trouble is that these techniques don't work very well or very often. I should say they work very well when they're applicable, but when they're not, then you're stuck. And so then we have to do some kind of analysis. Okay, but before we talk about the analysis, we're going to, the big idea, well, I guess we could talk about the big idea first. The big idea behind the analysis is that we will look at our plane, xy plane, and find out where the equilibrium solutions are. And one kind of rule of thumb that works pretty well is that most of the interesting behavior, interesting is in quotes, most of the interesting behavior is organized around those equilibrium solutions. And so what we do is then we locally analyze each equilibrium solution close by and hope that that's going to represent the big picture when we open it up. Okay, sometimes that does, sometimes it doesn't. We'll have to figure out when. Okay, but how do we do this local analysis here? Well, that's why we do the linear systems first. Okay, and so from this system, our ansatz says that x of t as a vector is e to the lambda t times v. And so if we plug that into our system, then we get that this is our coefficient matrix ABCD. AV equals lambda v, or we get that A minus lambda v1 plus bv2 equals 0, and cv1 plus d minus lambda v2 equals 0. So we want to solve this system of equations. This is the main equation that you have to remember. Okay, because this defines our lambda and our v. And so what we're doing here is we want to get non-zero v1 and v2 as possible solutions to this. The only way you're going to do that is if these two lines are actually multiples of each other. And the only lambdas that'll work in that case will be when the determinant of this matrix equals 0. Good. And then we had a shortcut for computing that. That's kind of handy, but it only, I want to emphasize, this only works for 2 by 2. So if you're going into linear algebra next, you won't be able to use this formula all the time. This only works for 2 by 2s. Okay, but it is handy because it tells us what our eigenvalues are in terms of the trace and the determinant of the matrix ABCD. Good. Where A equals ABCD. Good, and then we have our three cases. Our three cases is where so this is a quadratic, and so we look at the discriminant, which is b squared minus 4ac, or the trace of a squared minus 4 times the determinant. Okay, and so if the discriminant is positive, then lambda 1 and 2 are both going to be real and distinct. And so therefore our solution is a linear combination of our ansatz here. So that's going to be c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. Good. If the discriminant is negative, then lambda is complex. And we only use one of those. And so let's let v be the eigenvector. And so x of t is going to be a linear combination of the real part and the imaginary part of our expression. Real part of e to the lambda t times v plus c2 times the imaginary part of e to the lambda t times v. Good. And then if the discriminant is 0, that means that we only have one eigenvalue, or a double, lambda is double, a double root. Okay, the problem with that is that we only have one function, but we need two to form a fundamental set of solutions. And so therefore our x of t, we just came up with this trick, right? It's going to be e to the lambda t times our initial condition plus t times w, where, how do you find w? W is found by something similar to this, right? It's a minus lambda v1 plus b v2 equals w1 cv1 plus d minus, oops, you know what, that's x0 y0. I'm copying that instead of writing it. That's x0 y0. Good. All right. So notice that this is a particular value of W1 and W2 that you want to use here because our X0 is known and fixed, right? So this is not a generic solution. This is a single solution. This is one solution that satisfies your initial condition, X of 0. Good. All right. So that's all the linear system stuff. And again, once you find the linear system, then we're able to, I guess before we classify, we also classify the origin. And how did we classify the origin in the linear case? The Poincare diagram. I'm running out of space here. Let me flip over to the next page. So the Poincare diagram is based on what? Our discriminant, which was the trace of a squared minus 4 times the determinant of a. And so if that's equal to 0, in the trace of a determinant of a plane, we get this parabola. The parabola splits the plane into 2 pieces. And so in one piece, the discriminant will be positive, and in the other piece, it will be negative. So if you forget, for example, up here, you see that if the trace is 0 and the determinant is positive, the discriminant is negative. So inside the discriminant is negative, outside the discriminant is positive. Right, so inside is where we have complex solutions to our to our characteristic equation. That's what I'm trying to say. And outside we have our 2 distinct real solutions to our characteristic equation. Down here, we can be even further. We can go further. Down here we have all saddles. I should say the origin is a saddle, right? We're classifying the equilibrium solution here. And so in this region we have, I won't label them all, but we'll have, this is where the trace is positive. Excuse me. So we have sources here, sinks over here, centers here, spirals here, spiral source, spiral sink. Okay. And so it's always good to be able to locate yourself on the Poincare diagram in order to fill this out. Okay, I've only got 1 more minute, but the last piece we looked at was method of Nullclines. And in that case, what are Nullclines? Nullcline is where either f of xy equals 0 or g of xy equals 0. Okay, so just as a quick example, suppose that x prime is equal to 1 minus x squared. Y prime is equal to 3 minus x minus y. Then how would we find our Nullclines in the xy plane? Well, this one, the Nullclines would be x equals plus or minus 1. Excuse me. And then the second one, it's y equals 3 minus x. So we have x equals 1, x equals minus 1, and then 3 minus x looks like that. Oops. Sorry about that. Oh, I could make that 3. Oh, that's a 1. Not to scale. Okay. Those don't actually intersect right there. That's bad. Okay. Well, I'm running out of time. So I will stop here, and we'll do this as a detailed example later on. I don't want to cut myself off like I did last time. Okay, I'm going to stop here, and we'll talk more about the method of Nullclines when we get to that problem in the review.